Rachel Phillips was awarded an NIHR Doctoral Research Fellowship in 2018 to undertake her PhD at Imperial College London. Her research focuses on the reporting and analysis of adverse events in drug trials and developing statistical methods to better identify adverse drug reactions. Rachel is also a clinical trial statistician at Imperial Clinical Trials Unit. Rachel?
Thank you. Thank you for that introduction, and thank you, Tianjing, for inviting me to speak here today. Yes, over the next 15 to 20 minutes or so, I'm going to take you through a series of visualizations that could be used as an alternative to common contingency tables that we see presented in journal articles for adverse events or harms reported in individual RCTs. So hopefully I'll demonstrate to you how they can help improve how we communicate information on harm profiles in the RCT setting, but also getting you to think more carefully about how adverse event information in trials is summarised and presented, and how this can impact systematic reviews of harms, and how some of these ideas could actually be adopted into the systematic review arena. Just before I get started, I want to acknowledge that this work has been undertaken with my colleagues Victoria Cornelius and Susie Crowe at Imperial College. Okay, so to begin, I'm going to give you a brief background and reminder why analysis of harm outcomes in RCTs is not necessarily straightforward, and actually what it currently looks like. So RCTs, as we've heard, are typically designed around a primary efficacy outcome. So, for example, we might be interested in testing whether some new drug, A, improves survival compared to standard of care. And as for statisticians and clinical trialists, how we analyse such outcomes is well established. Now, as well as this primary outcome, drug studies will have many secondary outcomes, which can include known pre-specified events relating to harm. And then we also collect any emerging untoward or harmful medical events, and these get termed adverse events. Now, despite these being standard outcomes in trials, the way we analyse them are not well established. So why is this? Well, primarily because such outcomes are complex and analysis is not simple. Unlike our efficacy outcomes, which are well defined and limited in number from design, we don't know what or how many of these adverse events will be experienced. We also collect additional information on the severity of these events, the timing, how long they lasted, and whether they were repeat occurrences of these. On top of this, many of these events are going to be occurring at very low rates. So if you think about all of that, analysis is not going to be straightforward. So what do we actually do? So myself and colleagues undertook a review back in 2019 and found that trials typically simplify such outcomes in their reports. So they measure whether an event did or did not occur, regardless of outcome type, and then they further simplify it by reporting events as occurring to participants at least once, ignoring that information on repeated events. And we get this information presented in these 2x2 tables like this. Now, in addition, despite a lack of power to undertake formal hypothesis testing on these outcomes, we found that over half of the studies in our reviews actually undertook some hypothesis testing approaches. And then they went on to make conclusions such as these drugs were well tolerated or safe based on these assessments. So we're in a situation where we've got complex, multifaceted data that we're simplifying and presenting in 2x2 tables, sometimes accompanied with inappropriate hypothesis tests. So let's think, in our presentations of these adverse event tables, what are we actually trying to do? Well, we're trying to identify if there are any harms from this drug, or put another way, we're trying to identify signals for adverse drug reactions. So is there a causal relationship between the drug and the event? But reporting adverse event data in such tables is overwhelming, and it can obscure the overall harm profile and any signals for adverse drug reactions. We need to be presenting summaries that are more digestible and allow a clearer, more informative profile to be presented. So the question I pose to you today is whether visualizations offer a potential solution to this problem. So I'm going to take us through some case studies in the next couple of slides, and I'm going to focus on the most common situation we find ourselves in when analysing adverse event data, and that's the analysis of multiple binary outcomes. But these plots can be adapted in some circumstances to the different type of outcomes that we get. So first of all, here's the first case study. In 2020, Wang and colleagues undertook a randomized, multi-center, placebo-controlled trial of remdesivir in adults admitted to hospital with severe COVID-19. The results of this trial were presented in The Lancet. The trial had been originally powered to detect a change in time to clinical outcome within 28 days, but it was stopped early by a data monitoring committee with the reason stated that this was there were a higher proportion of participants discontinuing from the study treatment due to adverse events. And this was alongside the consideration of the improved control of COVID-19 in Wuhan. So in the paper, the authors included a table of adverse events that included all adverse events occurring in 2% of participants in either treatment arm, all serious adverse events, and all AEs leading to study treatment discontinuation. Then in the text, the authors listed the names of the most common events by arm, but there was no definition of most common provided. So this resulted in them reporting the 6 most common events in remdesivir and the 7 most common events in the placebo arm. But how useful this information is unclear, as they may not actually be clinically important events, or events where there was actually a numerical imbalance between arms. And in fact, on closer inspection, 5 of the listed events were the same in both arms. And without any other information, it wasn't actually clear if this could just relate to the underlying infection or the participant comorbidity. So what if we looked at this data visually instead? So this is a volcano plot for the section or the subsection of that table that were reporting adverse events that occurred in more than 2% of participants. So we've got plotted the risk difference against a log transformed p-value. Now, in the absence of any disproportionality in harm, we would expect a symmetrical curve with a random scatter of events centred around the null value of 0 risk difference. So in this plot, the x-axis is representing the difference in proportion of participants experiencing each event between the treatment arms. We've plotted the risk difference here, but we could present a relative risk or incident rate ratio or hazard ratio if suitable. The y-axis is presenting the p-value from a Fisher's exact test on a negative log 10 scale. The size of each of these bubbles is proportional to the total number of events for both treatment arms. And colour is being used to indicate the direction of treatment effect, with red indicating a greater risk in the intervention arm and blue indicating a greater risk in placebo. And then colour saturation is linked to the strength of the treatment effect corresponding to that p-value. And here we've chosen to label the 2 events where there's a suggestion of asymmetry in the plot, and we may wish to flag for further inspection. So the strength of the volcano plot is that it gives us an overall and an immediate representation of the adverse event profile and allows us to draw attention to particular signals of interest, but it's not allowing a detailed review of adverse events. We can see we've got a fairly symmetrical scatter for most adverse events in this plot, but there are perhaps 2 events that are asymmetrical. So the first here is this increased AST, which is occurring more frequently in the placebo arm. And then in remdesivir, we've got perhaps a signal for rash. Now, in the text, the authors reported on this increased risk of AST in the placebo arm, but there was no mention of the rash. So I think what we can see here is not reporting rash in the text for remdesivir demonstrates the subjectivity that there might be in describing adverse events like this, and actually communicating results in a visual way might perhaps provide a more transparent way to communicate this information. Now, alternatively, we could have presented this data in a dot plot. Now, this provides a way to simultaneously evaluate both the relative and absolute risk for each event. It includes a relative risk with the company and 95% confidence interval in this right central panel. And adverse events have been ordered from the bottom to the top by the increase in relative risk. Now, the 95% confidence interval in this plot can be used as a means to assess the precision of the risk and also the strength of evidence against a null hypothesis of no difference by examining the position of the lower or upper confidence interval bound in comparison to the value of no difference. But in fact, we would discourage interpretation of confidence intervals fixated only on whether or not they cross the value of no difference, because we've not powered these analysis for such hypothesis testing. And then we can see from here that the relative risks are fairly evenly distributed on either side of this vertical line of no difference. And in fact that the relative risk furthest away from 1 is for AST, so it aligns with the volcano plot. Now, on this plot, we can also see the corresponding absolute risks, which can be read from the left-hand side of the graph. And we've also included here a data table on the far right-hand side with the raw numbers. Now, this detailed information on absolute values can be especially useful in situations such as when the event rate is low. Now, in contrast to the volcano plot, we've got a lot more information in this plot, but it does require more assimilation to understand what's going on. Now, if we look at the volcano plot, looking at the subset of that table which was presented the serious adverse events, we notice that due to the lower event rates in serious adverse events, the volcano plot is harder to interpret, as what perhaps is not obvious is that there are a number of overlapping events that have the same risk difference and p-values, and therefore we can't uniquely see them. So we're also seeing here a highly asymmetrical pattern, highlighting a signal for both a higher risk in the placebo arm of cardiopulmonary failure and multiple organ dysfunction. Now, the prominence in this plot of multiple organ dysfunction is likely to be overemphasized given the extremely low event rates in this event, where there were 2 versus 1 events. So I think this is a nice example here where use of the volcano plot alone to draw inference could provide a misleading impression. If instead we looked at the dot plot provides a more accurate display of the serious adverse event terms, and it can be seen that the point estimates are generally more in favour of remdesivir than placebo. So we've got 13 relative risk point estimates lying to the left of the null value and 6 to the right. However, there is great uncertainty in each of these risk estimates, with most of them actually generously overlapping the value of no difference. And then on the left-hand side, we've got the absolute risk for each event, and we can clearly see that the risk is low for many of these events, with many of them containing 0 events, and this is confirmed with this data table. Now, looking at that final part of the table, so for discontinuations due to adverse events, we have a similar problem that we had for the serious adverse events due to the low event rates. But what we can see is that there does seem to be a signal here for harm in the placebo arm for serious secondary infections. And this event wasn't mentioned in the paper by the authors. Now, we can also see there's a signal here for respiratory failure, which was mentioned by the authors, but perhaps the strength of evidence for this is less than that for serious secondary infections. However, what we should flag here is that the plot can only display the numerical differences. It's not conveying whether serious secondary infections are of less concern than respiratory failure in this population, and therefore a smaller difference in respiratory failure may be of more importance than a greater one in secondary infections. Now, looking at the corresponding dot plot, the dot plot supports the same message as the volcano plot for secondary infections. You can see down here. But the higher rate for respiratory failure in the remdesivir arm is perhaps clearer to see in this plot, but what we can now see is that there is great uncertainty in this estimate, and that actually the event counts were very low, so we had 7 versus 1 events. So the volcano plot has the benefit here of an immediate communication of extreme differences in adverse event rates through fast and simple evaluation of asymmetry in the plot. It provides us with a way to assess the profile of adverse events without the detail, so it can be a highly effective way to communicate signals for adverse reactions. But it's less effective when there are fewer adverse events in total, or where several of these events share the same frequencies or the frequencies are very low. A disadvantage of the volcano plot, or another disadvantage, I should say, of the volcano plot, is its inability to incorporate the precision of the estimates. And we found that, and I've shown hopefully, that it was possible to give a misleading impression in some scenarios when the event numbers were small. So researchers do need to be cautious when constructing a volcano plot, and they need to check if the image actually conveys a fair representation of the raw data and the message delivered. Now, the dot plot, on the other hand, provided a very different way to communicate results compared to the volcano plot and allowed us to include more detailed information. But it does require more involved appraisal. But we could argue that this is probably shorter than trying to appraise a typical 2x2 frequency table. And in fact, I would go as far as saying that the dot plot could be viewed as providing a substitute to an adverse event frequency table. An advantage of this is we've got both an absolute and relative between arm comparison in this plot, but there is caution needed with inclusion of that 95% confidence interval, which could encourage an interpretation as a test of no statistical significant difference, which in turn may encourage false conclusions of safety and possible missed signals. I just wanted to highlight that both of these plots have been produced in Stata using user-written commands AE volcano and AE dot, and that there is a full evaluation of both of these plots in a recent paper in Trials. So now, before I wrap up, I just wanted to highlight that there has been some positive implementations of visualizations recently. So the Pfizer-BioNTech COVID vaccine trial reported results in the New England Journal at the end of last year. This was, I'm sure as many of you know, a multinational placebo-controlled randomized trial comparing two doses, 21 days apart, of either a placebo or the BNT162b2 vaccine. And the primary endpoint for this study was the efficacy of the vaccine against laboratory-confirmed COVID-19. The authors also reported on some pre-specified local and systemic adverse events up to 7 days post-vaccination. They also included unsolicited adverse events post 1 month, and then unsolicited serious adverse events post 6 months from the second dose. But looking at those local and systemic events, the pre-specified events, the authors chose to present this information in a stacked bar chart. Now, this is the bar chart for the subset of those aged over 55 after their second dose, but they did also include it for the other subgroups. Now, in the text, the authors comprehensively reported on this visualization, flagging that fatigue and headache were the most common events, and that fatigue, but for both events also had quite high numbers in placebo groups. And they also reported they also reported the frequency of any severe systemic events. Now, whilst I commend inclusion of this plot, I think based on some ongoing work looking at the stacked bar charts for incorporation of severity ratings for adverse events, we'd actually recommend something more that looks more like this. So flipping the bars from vertical to horizontal to make that comparison between arms a little easier. And we'd also recommend reversing the severity scale so that the most burdensome events could be directly compared between arms. So, for example, you can look at the height of the bars for the severe events between arms, but then you could also look at the severe plus moderate and see how that compares to the severe plus moderate in the other arm. We'd also suggest labelling these bars with the frequencies of events and not the percentages, as the percentages can be read off the x-axis relatively easily, and then the labels are actually adding more information and more detail that's missing from the published version. So I hope I've demonstrated how visual displays can provide an alternative way to communicate risk of harm compared to traditional frequency tables, and that they allow you to assimilate quite large volumes of data whilst encouraging an informal between-arm comparison. But I also hope it's clear that assessments of adverse event data in a review of a table or each of these different plots can provide a different emphasis, and that researchers still need to examine crude numbers alongside graphical displays. And I hope ultimately that better reporting of harms in individual RCTs will have a positive impact on systematic reviews, including harms, and incorporation of visualizations can potentially help flag potential harms of interest to include in future reviews. I know that these visualizations sometimes remove the numbers that are so important to systematic reviews, and of course they will still need access to this. So I think there is opportunity here to use the supplementary and registries for that. And just on a very, very final note, I wanted to flag that I'm currently developing a consensus of recommendations in conjunction with the UK CRC CTU statistics group for using visualization in RCT reports for the full spectrum of outcomes. So your binary, count, continuous and time to event outcomes, not just binary. And we're hoping to publish this sometime later this year. But in the meantime, if anyone wanted to contact me regarding this or this future work, please feel free to email me.